to implement a hybrid column level encryption in MySQL. Quick introduction. I have been working with MySQL for more than 15 years already. I started at MySQL AB in 2006 as a consultant architect. Been working for Sun Microsystems, Oracle doing MySQL consulting, working for Percona since 2014 as architect. I've been working with a smaller startup called Virtual Health, and recently joined Amazon Relational Database Services (RDS) engineering team in 2020. My interests are in Internet of Things, different devices, and in IT security as well. So today we will talk about different encryption method in existing encryption method. The problem with those encryption method is they may not provide adequate encryption for sensitive data. And I will be proposing a method of column level encryption, which will provide much higher level of protection for things like social security numbers or credit card information. And this will also work with legacy applications. Let's start with some background information and existing solutions for protecting data in MySQL. Usually when we talk about protecting data in MySQL, we talk about encryption. And encryption is required by different compliances like HIPAA or PCI. Amazon RDS have already have security features like encryption data at rest, encryption data in transit. But the problem is that some sensitive data may require some additional protection. Those are usually type of encryption that we use. We distinguish between data in flight and data at rest encryption. Data in flight is protecting the channel, the communication channel between the application and MySQL, and data at rest covers the disk encryption. When we talk about data at rest, we usually talk about full disk encryption, uh, transparent database encryption or TDE, and field level encryption. And our focus today talk will be on field level encryption. Usually, full disk encryption is very easy to implement, and there is almost no performance penalty. For example, on Amazon RDS or in EC2, you can enable the encryption by encrypting disk with KMS. It's very easy to do it. Just pick the option. Um, Other options exist for a full disk encryption on Linux with LUKS, for example. Or if you're using shared storage on premises, you can also use some sort of shared storage encryption. However, the problem with full disk encryption is that it only protects the physical access to disk. If MySQL is running, then data in MySQL files can be seen as unencrypted. So basically, it is encrypted only when volumes or disks are mounted. Uh, Not mounted, sorry. So another option will be to use transparent database encryption or TDE. TDE take care of encrypting database files, like in MySQL InnoDB files, like table spaces, redo logs, undo logs, binary logs, temporary files. So basically, all the files that MySQL uses will be encrypted. Finally, there is a possibility of doing a field or column level encryption. So column level encryption is basically an application code which will encrypt the fields that are needed to be encrypted. Such fields as, for example, PII information, personal identifiable information, or medical PHI information, or credit card numbers, or social security numbers. The problem with field level encryption is that it is hard to do it right. We need to think about key rotation. We need to think about the MySQL query overhead. We need to think about indexing and stuff like that. Here's a very quick overview with pros and cons of each encryption method. So full disk encryption is easy to implement and lowest of overhead. So those are the advantages. The disadvantages comes in how the data really encrypted and when the data is encrypted. So it only protects from copying database files pretty much. The transparent database encryption is better in this regard. It also pretty low overhead, but the main problem with the TDE is when MySQL is running, then data is already decrypted. So if someone will be exporting data like MySQL dump, then those data will be coming out as non-encrypted, as clear text. So the field column level encryption probably provides the best security. It provides the best protection. And also it can be combined with other options like full disk encryption. However, it requires some application changes, and also overhead can be significant in some cases. So now I will talk about the field level encryption and some of the implementation options. So again, when application encrypt and decrypt data in the code, the data is already encrypted. So we don't need to worry about data in flight or data at rest. However, the application need to implement encryption. So the application will be responsible for encrypting and decrypting the data. In many cases, uh, we have a legacy application, and the legacy application cannot be changed. Another problem with field or common level encryption is that we need to store and potentially rotate encryption key. And it can also complicate MySQL queries. Like if we use range scan or order by, it may not work uh, inside MySQL. Here's the, I will talk about one possible approach for MySQL to implement field level encryption for some fields. Here's our plan. We identify fields that will require an additional encryption. Such fields, again, as social security numbers, credit card numbers, or medical diagnosis, stuff like that. So then what we will do is we will create encrypt and decrypt functions as stored function. We can also use UDF, user-defined function. Then we will use a MySQL rewrite plugin and potential triggers to inject encryption into MySQL. And then finally, we'll use application level encryption key. So the application will supply this key and those functions will use it. Here's our possible implementation diagram. What we have on this diagram is that we have application and MySQL. Application will send the application code, in this case secret, but of course it should be something better than this. Then we will create this function, and on insert we'll use this function to encrypt the data. On select we'll use another function to decrypt the data. So what we'll need to do is we'll need to implement the myEncrypt and myDecrypt stored functions. How do we do this? But before we'll go into implementing the functions, let's talk about prerequisites. One of the most important prerequisite is that we have already implemented data in flight encryption. So application connects to MySQL with SSL TLS. That will protect sending over our encryption key and also will protect sending over the unencrypted data. Application should definitely store this key securely. When our prerequisites are filled, then we can start creating our encryption and decryption functions. This is probably the easiest implementation, pretty much a single line implementation of the function. So we'll create a function which will return binary. It's very important because it's pretty much bytes. And then we'll use a MySQL built-in function called IsEncrypt. Then this app key, application key, has been set as a session variable. And this session variable has been sent over from the application. Then we create another function called myDecrypt and do the opposite operation. We'll do IsDecrypt. How does it work? So the again application sends this app key on connection or before doing the encrypt decrypt operation, and then it will do something. It will call this function. Here's the example. So I do hex on myEncrypt and get the hex bytes out of the encrypted bytes. The reason I use hex is just not to display the characters that cannot be viewed. So then I do encrypt and decrypt, and then I get the original text. Let's talk about the security of this. So usually we will have three parts of the security. Let's think like what attacker will do. Um, an attacker can be in the middle, man in the middle, but that's okay. We already use SSL TLS to encrypt our communication channel. So we will not be able to see the key, and we will not be able to see the data coming to and from MySQL. Let's say that we have MySQL DBA or someone who attacked MySQL, um, who wants to see the sensitive data, but they will not be able to do that. They cannot decrypt the exported data, for example, because it's protected by the key. And then finally, if we look from this side, from the application side, an attacker will need a key to decrypt the data. And that may be one of the vulnerabilities points of this design. If an attacker will get the key, then this person may be able to decrypt the data. We'll talk about that later. Um, how does those things are being protected? Let's talk about the vulnerability points. So application level, key of course needs to be protected. And if you store in this key on disk, it's it's not good. Probably much better idea will be to use some sort of secure storage like AWS Secret Manager or some other options like Vault. And then the best option will be to load the key in application memory on start. So if, for example, an attacker will be able to take over the web server, they may not be able to read the key from memory. So that was application level, MySQL level. That's a little bit problematic because the key itself can be recorded in logs. Again, we do set variable equals something that can potentially be stored in slow query log, audit logs, performance schema, and stuff like that. Then someone will be able to potentially, someone with full access to MySQL will be able to record this. Now, how do we deal with legacy applications? Let's say we cannot change our application code. So what we can do is on insert, we can use trigger. And this trigger can create the can actually call the function, myEncrypt function. What about select? Selects can be handled by the query rewrite plugin. MySQL, starting with version 5.7, supports the query rewrite plugin. So we can actually rewrite the query uh, and create a pattern. For example, if we do select SSN from employers, then this SSN here will be changed. This SSN here will be changed to my decrypt function. Here's the example of the implementation. So here's our table, employer table, and we declare as SSN as blob here. It's better to declare as var binary, but we'll use the blob here in this example. So what we'll do is we will create a trigger, and the trigger will run just before insert on employers. And it will change our SSN to encrypted version of SSN. So then the application will keep doing what it was doing before, queries like this, and then it will be encrypted. So in this example, we will not be able to see the SSN, but we will be able to decrypt it. Now, the second thing that we will need to do to be able to handle the legacy application is to use the rewrite plugin. So the rewrite plugin will actually change this to this. Similar to trigger, where it will inject our function, we will inject our function on select. So then uh, when we implement the rewrite rules, we will be able to automatically decrypt our uh, data like SSN using the rewrite plugin calling the function. Some other operations on encrypted columns may or may not be challenging. For example, if we would like to do the select and use an index, will need to use this form. So instead of decrypting the field in MySQL and compare it to the decrypted column, we do the opposite. We will encrypt our social security number We'll encrypt it right here using the myEncrypt function. And then we will compare the encrypted data to the encrypted data. This is pretty much the only way how we will be able to use an index. In this particular case, we have created an index on SSN, then we have supplied our key, and then we run this select, and we can see that MySQL is indeed using an index here. However, other operations on encrypted columns may be challenging. One example is order by. If you do an order by, for example, you will really need to encrypt last name. Then what will happen is that MySQL will have to run a decryption because the order of fields is lost when we are encrypting it. So MySQL will have to pretty much do the full table scan, do the decryption, and then display it. So things like order by will probably not work out of the box. Now, you may be wondering what is the performance overhead of this? And to measure the performance, I created this very simple benchmark. The thing is, when we run a single query, then the performance overhead will probably be negligible because it's a single query, a single insert or single select. We will apply our functions, and we will not be even be able to measure that. However, for the bulk operations, that is completely different. For the bulk operation, we can see that the overhead is quite significant. It's up to 2x slower. So if you're using the bulk inserts, or if you were thinking about implementing the field level encryption like this, then it is important to test it out to benchmark it. So finally, we'll go through the field level encryption implementation pros and cons. So the pros, the advantages, is significantly higher level of security for sensitive data. Data is encrypted even when the database is running, compared to other methods where usually when MySQL is running and you are able to connect to MySQL, the data is displayed as not encrypted. Also, it's compatible with other encryption methods, and the proposed implementation can work with a legacy application. Almost no application changes are needed. The only change that may be needed is to set the key. That can be done on connection, on establishing connection. So it probably be much easier to implement for legacy application compared to other options. However, we will need to be careful when implementing it because some of the queries may be significantly slower. For example, the select with order by, for example, again, if we're encrypting the fields that needs to be sorted, like, for example, first name, last name, then the order by operations will be significantly slower. The range queries the rank queries also will be much slower. You will have to decrypt the field before running the range query. For the insert updates, implementing with triggers can be 2x worse. This is an additional operation running from the trigger can actually make things worse performance-wise. So it's important to benchmark before implementing. Finally, two other things. Key rotation will require re-encryption. So if we need to rotate the key, we'll have to go and re-encrypt all the fields that are currently encrypted. And also, there's still some vulnerable point from MySQL uh, side. A query can be recorded in the logs. A query can uh, be shown even in show process list, for example. It can be visible in performance schema and stuff like that. So those are the downsides. There are some other options of implementing similar things. MySQL supports from version 8, MySQL supports the keyring, and it now supports the secret field. There's a very good article here on how to implement asymmetric encryption and using the secret keyring. Although this will it's probably a little bit different use case. Finally, the summary. So we have discussed, I have proposed the mechanism, the architecture for the field level encryption, and the goal of the field level encryption here is to protect the sensitive data. It can work with other encryption method. It can work together with a full disk encryption, for example, and provides better security with minimal application changes. The downside of that is that some queries will be slower and you will need to test and benchmark. And some queries may not work as expected. So that's all that I wanted to talk to. Now it's time for questions. Thank you very much.